Have you ever wondered how AI actually understands what it's saying? It's not just about matching keywords, it's about genuinely grasping meaning. The secret lies in something called embeddings. In the next few minutes, we're going to break down exactly how embeddings work, and don't worry, no math degree is required. Let's start with a simple sentence. The cat sat on the mat. To a computer, that's just a series of characters pretty useless on its own. The first thing we do is tokenize the sentence. This means we split it into individual units called tokens. Each token is assigned a numerical ID which serves as the raw input for a neural network. Though each token doesn't have to be a full word, we'll consider them as words for simplicity. These tokens are then fed into a transformer neural network like BERT or a sentence transformer. This model has been trained on billions of sentences. Through this training, the model has learned the patterns of language, including grammar and context, as well as which words tend to appear near each other. As your sentence moves through the network, a signal flows through each layer, refining and compressing the meaning at each step. The attention layers play a crucial role here. These attention layers help the model learn which words relate to each other. So, what's the output of this process? It's not text but numbers. Specifically, you get a list of 768 numbers called a vector. This vector represents your entire sentence as a single point in a mathematical space. Keep that in mind. We'll return to that thought. Here's where it gets interesting. Because the model was trained on real language, similar meanings result in similar numbers. Those similar numbers end up being close together in space. Let's see how it works. We start with the sentence, "The dog is playing at the park." A single dot appears in the space. Now consider a puppy runs through the grass. Completely different words, yet notice where it lands. The dot appears nearby, indicating closeness in meaning. The model has learned that dog relates to puppy and park relates to grass. It's the same concept in the same neighborhood of space. Now, let's consider another example. The stock market crashed today. It's a totally different topic. Here, the dot appears far away as it should. The model isn't just matching keywords, it's matching concepts. Sentences about animals cluster together, while sentences about finance also cluster together. The closeness between two vectors is measured with something called Cosine Similarity, which is the angle between them. A small angle signifies similar meaning, while a large angle indicates a different topic. Now let's look at a list of sentences and their Cosine similarities. You might wonder why a smaller angle means they are more semantically similar, yet they show a high value when close to each other. That's because we're calculating the cosine of the angle. So, a smaller cosine means a larger angle, and conversely, a smaller angle means a larger cosine, signifying similarity. A large angle with a smaller cosine indicates dissimilarity, such as between dog and park versus stock market. We can observe the actual values here. Now let's compare various other sentences. We took dog in the park as a primary sentence and compared cosine values for each. Now we'll examine puppy in the grass. You see it there, and we apply the same analysis to dogs outdoor and stock market. Notably, sentences like investors panic and stock market appear close together, but they're far apart from dogs outdoors. We'll do the same for investors panic. Now, let's move to a medical example. I'll plot all the medical terms onto the same graph. Here they are. So, if I ask what causes heart disease, and a document states cardiovascular factors include, this forms the question and the document provides relevant answers. Here, there's zero keyword overlap, so a traditional search fails. However, an embedding-based search works perfectly because the meanings align even when words don't match. That's the power of embeddings. Remember, a sentence gives you a vector. That's fantastic. Now imagine having a knowledge base with thousands of documents. That's millions of vectors which can't be stored in a regular database. A traditional database searches by exact match. You need a specific ID or keyword and that's it. But our requirement is different. We need to search by nearest neighbor. Find the vectors closest in meaning to the query. This is where a vector database comes into play with tools like Pinecone or ChromaDB. These databases are designed to store and search high-dimensional vectors on a massive scale. Before storage, a document is chunked into smaller overlapping pieces. Here's a paragraph from a medical document and watch how the chunker works. This is how the chunker splits it into three self-contained ideas, each one embedded independently. Why is chunking important? Because you want to retrieve the precise piece of information later rather than an entire 10-page PDF. Here is the complete ingestion pipeline. A document comes in, gets chunked, each chunk is embedded into a vector, and then the vector is stored in the database and indexed for fast search. This usually happens before any user even asks a question. Now, when a user asks, what causes heart disease? Just like in our previous example, the question gets embedded with the same model used during ingestion. So both are in the same vector space. The query vector is sent to the vector database. It performs a nearest neighbor search to find the stored chunks with the highest Cosine similarity, as we discussed earlier. The top results are retrieved and sent to the LLM as context, and the LLM reads these chunks to generate a grounded, accurate answer. That's how retrieval works in RAG. Let's recap. A sentence goes through a neural network, becomes a vector, a point in space. In this space, similar meanings cluster together, and a vector database lets us search this space at scale, identifying the most relevant chunks for any question. That's embedding, the quiet engine beneath almost every modern AI application. If this video resonated with you and you're eager to learn more, we're hosting a free live workshop on April 4th called RAG Explained, the architecture behind agentic systems. You'll grasp the full RAG architecture, the patterns used in modern AI copilots and agents, how teams engineer these systems at scale, and what it really takes to ensure retrieval is reliable in production. You can find the link in the description.